All right, let's jump right into this explainer and take a look at exactly how scientists are gearing up for NASA's upcoming Nancy Grace Roman Space Telescope. It's honestly one of the most highly anticipated observatories in a generation, and for very good reason. We all know and love Hubble, right? Well, Roman boasts a field of view that is 100 times larger than Hubble's. It's fully expected to revolutionize our understanding of everything from the mysterious nature of dark energy all the way to discovering thousands of brand new exoplanets. But pulling off a scientific revolution of that scale takes a monumental amount of preparation. Before this massive observatory even gets close to the launch pad, an incredible foundation of groundwork is being laid right now, right here on Earth.
It sounds completely impossible, right? I mean, how do you ensure astronomers can just hit the ground running on day one when the actual hardware is still sitting in a clean room? This is the ultimate puzzle for space enthusiasts and software engineers right now, planning the absolutely perfect observation before the telescope is even in space. The secret to pulling this off lies in a seriously robust ecosystem of specialized software, hyper-realistic simulations, and intense community prep. We are essentially building a digital twin of the cosmos just to practice on.
To understand how this all works, we're going to walk through the blueprint, simulating a virtual universe, calculating the perfect exposure, planning the cosmic survey, and finally, diving into the Roman research nexus.
Now, to really appreciate the massive planning involved here, we first have to understand the major paradigm shift in how this observatory actually functions. Roman is fundamentally a wide-field survey telescope. Think of it as painting broad cosmic canvases, rather than taking isolated little snapshots. Telescopes like Hubble or the James Webb Space Telescope are incredible, but they act almost like highly specialized sniper rifles, zooming way in on one tiny specific target. Roman's wide-field instrument is a totally different beast. It captures massive regions of the sky in a single sweep, literally almost half a square degree at a time. Because every single time you open the shutter, you're capturing an overwhelming amount of the universe, it completely changes how we plan our observations.
So first up is the blueprint, which is being spearheaded by the project infrastructure teams.
These teams, known as the PITs, are the ones laying down the foundational software and data pipelines to explore things like weak lensing, dark energy, and cosmic expansion. Hundreds of scientists are grinding away right now, building the highly specific tools we need to squeeze every last drop of science out of the Roman data. Just to give you an idea, the High-Latitude Imaging Survey team has the staggering job of figuring out how to measure the shape of billions of faint galaxies to an accuracy of 1 part in 1,000, just so we can map the dark universe. Meanwhile, the Galaxy Redshift Survey team is busy building pipelines that use baryon acoustic oscillations and redshift space distortions to track dark energy. And the Supernova Cosmology team? They're writing algorithms to automatically spot Type 1a supernova all the way out to a redshift of 3, helping us measure exactly how fast the universe is expanding.
And because Roman covers so much cosmic real estate, a massive 75% of its initial 5-year mission is carved out for predefined core community surveys. This is specifically designed to maximize the science return for absolutely everyone. We're talking huge, unified efforts like the High Latitude Wide Area Survey or the Galactic Bulge Time Domain Survey. The real beauty of a wide-field telescope is collaboration. One single sweeping observation is so incredibly rich with data that it can easily serve 50 different scientists working on 50 totally different research goals, all at the exact same time.
Which brings us to what is quite literally a game changer in astronomy today. Roman will have exactly 0 days of proprietary data, period. Historically, astronomical data is fiercely guarded. If you want time on a major telescope, you typically got a year or so to analyze your data in complete secrecy before anyone else was allowed to see it. Roman is shattering that tradition entirely.
The second the data hits the archive, it belongs to the world. It is a total democratization of astrophysics. Whether you're a lead researcher at a massively funded institution or a high school kid teaching yourself Python in your bedroom, you get the exact same access at the exact same time. The playing field is completely leveled. But, that raises a pretty interesting question. How on earth do you practice your analysis scripts for open data that hasn't actually been collected yet?
Well, that takes us to part 2, simulating a virtual universe, or as I like to call it, the rehearsal.
To rehearse, teams are using an insanely powerful software tool called roman-ISIM. Basically, it's a Python-based image simulator built around the well-known GalSim toolkit. Using open universe data, they simulate these incredibly realistic cosmic images. They even go as far as injecting actual known Gaia stars into the simulation to test astrometric precision, effectively anchoring this virtual universe to reality. They're literally rendering massive virtual chunks of the cosmos, complete with detector noise, cosmic rays, and subtle optical distortions. It's basically a hyper-realistic flight simulator for astronomers to rigorously stress test their data pipelines before launch.
And once we have that virtual universe, we have to properly process it. The onboard detectors are constantly taking continuous infrared reads, which generates an absolutely staggering amount of raw data. To handle this, the pipeline compresses millions of individual infrared reads into much more manageable groupings called resultants. It's a whole multi-step process that turns raw voltage building up on a sensor into a beautifully calibrated image of galactic light. Understanding exactly how this data compression works onboard the spacecraft is absolutely vital for any astronomer wanting to push the hardware to its mathematical limits.
Moving right along to the third step, calculating the perfect exposure, the calibration phase. To get the most out of any observation, we need to find that perfect Goldilocks zone for light intake, and we do that using the exposure time calculator, or ETC. Think of the ETC and its multi-accumulation, or MA tables, kind of like a photographer's highly advanced light meter. These tables dictate exactly how those reads are grouped together. For example, if you see a configuration like IM1358, that simply means imaging mode, a 13-second exposure, grouped into 8 resultants. If you point at something way too bright without selecting the right table to manage that light, your pixels will fatally saturate and completely ruin the data. The ETC lets you safely test these exact configurations in the virtual environment first. The ETC also proves exactly why choosing your instrument is absolutely crucial. When you run a simulation, you might find that using a standard prism ends up blending incredibly close emission lines together into a single totally unreadable peak. And for a scientist, blending is terrible. It obscures the crucial chemical signatures they're looking for. But if you switch to the GRISM spectrometer in the simulation, you can see it cleanly resolves those tight emission lines, like perfectly separating the 1.46 and 1.47 micron lines. You know instantly if your chosen instrument can actually do the job, or if you need to go back to the drawing board. Also, if you're hunting exceptionally faint objects out in the deep cosmos, the ETC is definitely your best friend. It can tell you in a split second that a super faint 21st magnitude galaxy captured in the Wide Area Survey's F1580 band will still give you a gorgeous signal-to-noise ratio of 37. To put that into perspective, achieving a ratio of 37 on an object that incredibly dim is remarkable clarity. It means the object is going to stand out beautifully against the background noise of space. This gives proposers the mathematical confidence they need to justify their science cases. You know with absolute certainty what Roman can and cannot see. All right, part 4, planning the cosmic survey, mapping out the flight plan. Armed with our perfect exposure calculations, we use the Astronomer's Proposal Tool, or APT, to plot the actual flight plan. Because Roman is a survey telescope, we aren't just picking a single star from a drop-down menu. No, we are importing complex CSV polygons, defining massive mosaic overlaps, and setting up intricate pass plans. This includes cool techniques like dithering, where the telescope makes tiny little shifts between shots to smooth out detector artifacts. You can even link observations to create cosmic time lapses. Say you're hunting for exoplanets, you can literally instruct the telescope to return to the exact same spot at the exact same orientation every single 5 days on a rigid schedule.
But planning your dream survey brings up a pretty massive puzzle: scheduling conflicts. Your custom flight plan has to be actively checked to make sure it doesn't accidentally collide with one of those massive, unmovable core community surveys we talked about. Remember, you're competing for time and space in a highly complex, moving 3D environment. With surveys like the Galactic Bulge program locking down the telescope's schedule for 70 days at a time, finding an open window is really tough. Thankfully, the software's built-in visit planner instantly checks your strict constraints and tells you precisely when your target is actually visible and clear to observe.
Finally, our last stop, the roman-research-nexus, the cloud. This is the ultimate destination for the impending cosmic data avalanche, and it completely flips the script on how we do astronomy. It moves the researcher directly to the data rather than trying to move the data to the researcher. Roman is going to generate so much raw information that it's going to operate on a petabyte scale. To truly wrap your head around that, consider this. Trying to download a single petabyte of data on a standard gigabit home internet connection would take you several months of nonstop downloading. Downloading the whole archive to a local machine, that would take lifetimes. It's just not physically feasible to do it the old-fashioned way anymore.
Instead, the Nexus hosts the whole shebang in a massive Amazon Web Services cloud environment. And the absolute best part? It comes fully pre-configured. Highly complex simulation and extraction tools like Roman iSim, Pandaea, and the Roman Image Simulator tool, or RIST, are already installed and ready to go. You entirely bypass the hours of pulling your hair out over local software configuration. You just open a browser window, log in, and boom, you instantly have access to petabytes of calibrated data. You and your colleagues across the globe can write code and analyze light curves collaboratively in shared Jupyter notebooks right there in the cloud.
The level of preparation for this observatory is truly unprecedented. The software tools are fully operational, the virtual simulations are running hot, and the entire community is building the infrastructure today to answer the biggest questions of tomorrow. So, I'm going to leave you with this to think about. When the keys to the absolute biggest public data set in the universe are finally handed to you, with zero proprietary delays, where are you going to point Roman first? Thanks for joining me for this explainer, and keep exploring.